This
to the UART
conference
block.
will now be recorded.
Left. So we will first discuss things with respect to the UART block and then proceed with the next communication protocol. So we first got to know the features of the UART block, which is available on our microcontroller. It's an asynchronous protocol which achieves any duplexity, and we refer the terminologies as in fact, not master and slave, we refer them as host and devices. So in order to achieve the, let's say, full duplexity, we need two data lines, one for the sake of transmission, the other one for the reception. So this is how the hardware connection happens between the two devices if they have to communicate with the help of the UART block. Then we saw the frame format. We first transmit a start bit, then 8 data bits, 1 parity bit and 1 stop bit. Then after that we understood what is baud rate, and we have to make sure that both the transmitter and the receiver are agreeing to work with the same baud rate. We saw the we saw what happens if the same baud rate is not agreed between the transmitter and the receiver, and then we saw what is the difference between the baud rate and the bit rate, how are they correlated to each other. Now after this, the next we have got to discuss is about the programming part. So first, in case of the programming part, we started with the configuration. Let me first open the representation. So here it is. You are stuck. Okay. So we tried establishing the connection between the laptop and the PiximLab board. PiximLab board has the PIC16F877A microcontroller. So whatever laptop is transmitting, that has to be received by the PIC microcontroller, and the same has to be transmitted back to your QTCOM application, which is installed on your laptop. Now, RC7 pin of the microcontroller acts as the receiver to the UART block, and RC6 pin of the microcontroller acts as a transmitter to the UART block. Now, whenever you are trying to transmit whatever data you want to transmit, you first have to write it into the TXREG register. Then the data gets shifted to the TSR register. Then data gets transmitted bit by bit from this TSR register via the RC6 pin of the microcontroller. So whenever I have to transmit some data, I'm going to call the putchar function. So we saw the definition of the putchar function. So here is the definition of putchar. Whatever data I have got, that is returned to the TXREG register. I'm waiting till TXIF falls down to 1. The moment TXIF falls down to 1, it is a confirmation that my data from the TXREG register is returned to the TSR register. And after that, data gets transmitted bit by bit. So for my next operation, I have to make TXIF back to 0. So that is the task. Then if I have to transmit more than one character at a time, I can call putS function. I'm going to pass the string as an argument. We are going to receive it as a pointer. Why only do while? You can either use a while loop, you can use a for loop, you can use a do while loop, any of a loop. So in first case, we have taken while, in the second case, we have written a do while. So just to show, there is nothing specific as such. Okay. Like RC6 and RC7 for the microcontroller, any pins from the laptop's transmitter and receiver. So obviously our laptop, the motherboard has the microprocessor inside it. There's a processor there. Now when it comes to the processor, to know what is the receiver and the transmitter pins of that processor, we have to open the data sheet of that processor, look at the communication being established. So for that we are using COM1. Okay, as a pair we are using COM1. So like you can check to which pin COM1 is connected. You can, if you go in detail, you can If you look at the data sheet, what COM1 represents, to which pin the COM1 represents, you can know, but you need the data sheet of the processor. Okay, fine. So coming to the put char, as I said, it is to write one character. So for multiple characters, till the character reaches null, so I'm going to call the put char function itself one character after the other. Now, similarly, whenever I have to receive the data, so you know that when the reception is happening, when I have to receive the data via RC7 pin, all the data gets returned to the RSR register. So the 8 bits of data is stored in the receive shift register. Then after 8 bits of data is collected and stop bit is identified, the RSR is going to write the 8 bits of data to the RCREG register. So whenever the data gets returned to the RCREG register, RCIF will be falling down to 1. So RCIF will be set to 1. So the moment I see RCIF is returned with the value 1, I'm going to read the data from the RCREG register to know what data it is. So whenever I'm going to read, I'm waiting till RCIF falls down to 1, RCIF is made back to 0. So whatever is the data in the RCREG register, that is returned. So you are going to collect it into a variable of 1 byte. So I'm collecting into a variable called CH. Now actually there is a small problem with this. Okay. So getChar is a function which is used to collect the data. PutChar is a function which is to transmit the data back. So these are the functions which are used by your microcontroller. Now assume I have one more logic apart from transmitting and receiving the data. Assume I have a logic to toggle the LED as well. Okay. So I have written a non-blocking delay so that the other statements are not getting disturbed. So there is a non-blocking delay written and I am going to toggle the LED. So I have taken this block just to show you that there must have been some other operations also to be taken care of. So as of now, I have a simple task to toggle the LED apart from transmitting and receiving the data. Now observe what happens. According to this, the LED has to be toggling by itself. So according to the logic, the toggling of the LED should happen. Now observe, I comment these two functions. Okay, I'm going to build this. So just to show you, the toggling of the LED happens normally. So I'm opening the PixSimLab board. Let me load the hex file to it. So before that, I'll wait for a few seconds to get the build completed. Okay, so it is giving me some warnings as the functions are not called, but let me ignore that. So now it says build has been successful and loading is completed. So let me go to the file, load hex, and load that hex file. So this is the file I have loaded. Can you see the toggling of LED? The brightness is a little less because the toggling is comparatively happening on a little faster rate. But still, can you see the toggling of LED is happening? Okay. Now let me change one thing. I commented the getChar and PutChar function. I will uncomment it. Let me put it in my code. Okay. So now in my logic, when I enter into the while of 1, after I do the initialization and all, when I enter into the while of 1, I'm calling a getChar function. So when will I call a getChar function? When do you think I will be calling a getChar function? Yes, I want to read a character. So I want to take the data. So your QTCOM has transmitted the data that is already received by your microcontroller. I have to get the data. Please don't incorporate it with the built-in getChar function. So this getChar is completely different. So your QTCOM has transmitted the data. Your microcontroller has received it. And whatever data it has received, it is collected in the RCREG register now. So getChar function should just take the data from the RC/REG register and give it into the user variable called CH. Okay. So now I have called getChar function. Now control will go to the getChar function. Now first of all, in case of getChar function, the very first thing I have written is while RCIF is not equal to 1. So I will be able to come out of this loop only when RCIF will be 1. And when do you think RCIF will be returned with the value 1? When will RCIF get returned with the value 1? All the bits are stored in the RC/REG register. Yes, when RC/REG register gets the data. Now, for the RC/REG register to get the data, user has to enter something from the QTCOM, right? For RC/REG to get the data, user should enter something from the QTCOM. Now, let's say user is not entering anything from the QTCOM. So, RC/REG will not receive any data. At that point of time, do you think RCIF will get any value 1? So if user is not entering anything, no, RCIF will not get any value. In that case, don't you think until the user enters a character, I will be stuck inside this while loop itself? Until user enters the data, I will be stuck inside this while loop itself. Now, even after user enters a character, so you will come out of the getChar. Anyways, CH receives that character. Then putChar transmits that character back. Now, this weight is initially 0. Weight minus minus is equal to 0 is fine. So toggling of LED happens for the first time. Again, you call the getChar function. You are stuck inside RCIF is not equal to 1. So you have to enter a character, only then you come out of the getChar function. Then putChar transmits that character. Now this logic works for every how many times? This toggling of LED happens for after how many iterations? Yes, after 50,000 iterations. Now if I want me to have this logic executed, don't you think I have to enter 50,000 characters? Because every time I'm getting stuck in the getChar function, I enter a character, only then I can come out of it. Then I have to check for a logic. So I literally may have to enter around 50,000 characters in order to get this logic executed. Now, do you think user has that much of patience to enter 50,000? Yes. And here I'm continuously monitoring RCIF. I'm continuously checking whether RCIF has fallen down to 1 or not. So what is it called as? If I'm continuously keeping an eye on the pin of the microcontroller or a bit of a microcontroller, yes, it is polling. Now, due to this polling, I am not able to pay attention on the other things. So RCIF is continuously returned with unless RCIF will not get returned with the value 1, I will be stuck inside the while loop itself. Now, how to overcome the drawback of polling? I have to make use of interrupt. Now, if you remember, RCIF is a name of an interrupt. It is receiving interrupt flag bit. Okay. So RCIF in fact is a receiving interrupt flag bit. So what you can do here is, instead of waiting till RCIF, yes, this is also a source of interrupt. So receiving is having one source of interrupt, transmitting is having another source of interrupt. Okay, so RCIF is not, instead of me keeping an eye on the RCIF bit, so I will configure it as a source of interrupt, and whenever an interrupt occurs, I will have to take the necessary action. Now observe what I can do is, from my main function, okay, so this is my main function. Okay, now here I'm not going to transmit any character. Okay, so I'm not going to transmit any character. Does interrupt depend on the RSR or TSR? See, there is one source of interrupt that depends on receive shift register, and uh, one more flag bit associated to transmit status register. So this is receiver's interrupt flag. This is transmitter's interrupt flag. So UART has two sources of interrupt. Okay. All right. Now I'll come to the main function. See, I will receive a variable called CH. Okay. So I will take a variable called CH. Now I take it as a character variable called CH. So being inside my while of 1, okay, I will take care of all other logics. Whatever logics I want to perform, so I'm going to have it return inside my while of 1. Okay, so inside my while of 1. So now what I have to do is, I don't want to call the getChar function. Okay, so I don't want to call the getChar function. Instead, whenever an interrupt occurs, what happens? If a source of interrupt occurs, where is the control going? Yes, control will go to the ISR function. So I will read the data in the ISR function. So first, the return type of the function is void. Function's name is ISR. Function also doesn't take anything, so it is void. Now first thing, after I come to the ISR, what should I do? After I come to the ISR, what should I do? If the user has entered any character, so that means whatever character user has entered via the RC6 pin, data is first received. So then it is returned, sorry, RC7 pin, data is first received. Then it is returned to the RSR register. From there, data is returned to the RCREG register. Then an RCIF will be set. So I have to first check if I came to the ASR because of the RCIF bit. So I'm going to update here. So I say if RCIF is equal to 1, correct? So the moment RCIF is equal to 1, what does it represent? The moment RCIF is returned with 1, what will it represent? It represents that the data is received. So where is my data? Where is that data? Whatever the controller has received. So where is that data right now? It is in the RCREG register, correct? So RCREG register has the data. That is what it represents. So my task is to just take the data from the RCREG register. So here I enter into the if block. I collect the data from the RCREG register. Then I'm going to make RCIF back with the value 0. Okay. So whatever is in RCREG register, I took it into a variable called CH. Now CH was a variable in the main function. If I want it to be visible in the ISR function, what should I do? Yes, I have to use extern char CH. Okay, so I have to collect it into CH. Now, whatever CH has received, what should I do in my task? Whatever CH has received, what should I do? According to the logic we have learned, what should we do? We have to transmit it back. So I call the putchar function by passing the CH back. Okay, I will not call the getChar function. I will read the data only if user has entered. So if user has entered, RCIF will be set to 1. Okay, so that RCIF, I have to check if I came to the ISR because of the RCIF. Then I'm going to read the data from the RCREG register. So ISR is a void function. I cannot return anything from a void function. So whatever is inside RCREG, I have collected into a variable called CH. Now ch is a character variable which I have taken in the main.c file. To make it visible in the ISR function, I have to bring it with the keyword extern. Are you able to follow this? Okay. Now initially, if user has not entered anything, what will be inside ch? Initially, if user has not entered anything, what will be inside ch? Is that a garbage value? What type of variable is ch here? It's a character variable, right? But the scope is, it's a global variable, isn't it? Now, what is the initial value of any global variables? Yes, it is 0. So, character ch is having 0 right now. Now, even if it is 0, do you think I'm supposed to transmit that character? See, assume I don't have any character entered. ch is initially 0. That means a null character. So you enter inside while of 1, you are transmitting a null character. So you keep transmitting the null character again and again. If it is not a null character, do you think it makes sense to transmit? No. So what should I do? How to avoid it? How can I avoid this? If it is, yes, I have to take a if condition. So if ch is not equal to, it's not uppercase null you're writing, it's character null. Okay. So if ch is not equal to character null, only then I'm going to transmit that character. But there is still a problem. Now assume ch is having null initially. Okay. So not equal to null is condition false anyways. So I'm not going to enter into the if block. Okay. Then next time assume ch is still null itself. So not equal to null is condition false. I don't enter. At some point of time user enters a character. So that character gets returned to the RCRDG register and the flag bit will be set. Control will come here. Now assume the RCRDG register has collected as character A. Now that character A is stored inside ch, then you come back to the main function. You are going to transmit character A, correct? So you are going to transmit character A. Now, after that you again come back. What is the value of ch? What is the value of ch after character A is transmitted and you come back here? What is the value of ch? It is still character A. Now, do you think I have to again transmit character A with the help of putChar function? No, right? So once I am done transmitting character A, I have to transmit the next data only whatever user enters. Now, how to make sure I don't pass character A again for another time? Until user doesn't enter another character, it keeps transmitting character A itself. How to avoid that? Any idea of how to avoid it? Okay. ch will again become null. Yes. So once you are done transmitting the data, what if I make ch back to null? Don't you think this will work? If I make ch back to null, for the next time ch will not equal to null will be condition false. You don't transmit. Only if the user enters another character, one more time ch collects another character, then you are going to transmit that character. Okay, so that is how you are going to achieve the interrupt method. Now see, I'm going to close this first and open a new project. Okay, so now observe this project. Okay, so source files, I'm showing the main function first, and also when I'm using UART's interrupt, what should I make sure to do? When I'm using the interrupt source, there are two sources in the UART right now. So what should I do? Yes, so I should not forget to write global interrupt enable return with the value 1. And for UART, you also have to make use of peripheral interrupt enable also. So both of them have to be returned with the value 1. So initialization of LED is done. Initialization of UART is done by passing 9600 as an argument. So nothing is different here. Okay. So I have everything SP and return with the value 1, CRE and return with the value 1, then baud rate generator, then receive interrupt enable bit. So there is one more bit which is used to enable the receiver. So receive interrupt enable bit is there. So RCIE is returned with the value 1. Then coming back to the main function, I'm transmitting UART test code. So you can see the logic init config. So ch is not equal to null. Then putchar function of ch. Ch is returned with null back. And this is the logic to toggle the LED. Then coming to the ISR function, I first check if RCIF is equal to 1. Then I collect RCREG value into CH. Okay. Then RCIF is returned with the value 0 back. And this is to check if the overload error is happening when you are transmitting the frames one after the other. And can you explain why CH is equal to null? Okay, I'm repeating again. So CH right now, initially, actually I have taken CH inside the ISR, and to use it in the main, I'm using extern. So it is completely up to you where you are going to take it as extern. Now, whenever user has entered a character, control will go to the ISR. CH is going to receive that character. Now, after CH receives a character, let's say it has received character A, okay, that character A gets transmitted. Now, assume this line is not there. So, you toggle the LED, you again come back here. What will be the value of CH? Once character A is transmitted, what will be the value of CH? It will still be character A, and character A again gets transmitted. Then again you come back, CH still remains to be character A. Character A again gets transmitted. Until you enter a new character, CH keeps transmitting character A itself. For one time I have entered character A, CH keeps transmitting character A till a new character gets entered. So that shouldn't happen. If I have entered character A for once, I have to transmit it for only once. So that is why I'm writing CH back with null. If CH is returned with null back, for the next time if you come, CH will be equal to null, condition will be false, you don't transmit the character again. CH is equal to yes, initially 0. That means we haven't done any initialization. So CH by default will have not character 0. So it is integer 0, which represents null. Okay. And what is overload error? We discussed in the previous class. So if you try transmitting the character, if you try transmitting a frame again and again, and the receiver is not able to accept the data continuously, it is going to give you an error shown. So that is an overload error. So the receiver will say that the data is being overloaded and it is not able to collect the data. So that's a overload error. UART interrupt is there in datasheet. I'll show it. We kept continuous equal to 1, right? Then it will accept. Sorry, continuous equal to 1. Yes, so we have written continuous reception with 1. That doesn't mean you can keep flooding the data without giving proper time for the data to be received. So you cannot continuously flood the data. So if the transmitter is continuously pushing the data one after the other, then receiver will not be able to receive it, which is why you will be able to not receive the data properly. Okay, so you can see here RCIE and TXIE. So they are the two bits. Okay, so they are the sources of interrupt. So if you see IE and IF, obviously they are the common names given for flag bit and enable bit. So if you are going to configure the receive interrupt enable bit, receive interrupt flag bit, then you have to enable it by writing RCIE with the value 1. If you want to make use of transmitting interrupt flag bit, then you have to enable it by writing TXIE with the value 1. Okay. So you can see here, transmitter, receiver. Okay, you can see here, if the transfer is complete, the flag bit RCIF is set. The actual interrupt can be enabled or disabled by setting or clearing the enable bit RCIE. So that way you will find the data in the data sheet. Are you able to get this? Okay. Yes, RCIE should be returned with the value 1 to enable it. Okay, fine. So let us continue here. The flag bit TXIF will be set regardless of the state of the enable bit and cannot be cleared in the software. So this you can see. See, transmit enable bit, transmitting interrupt enable bit need not be used. So you don't have to get an interrupt generated when you have transmitted the data. Okay. So you just have to know obviously that the data is transmitted. You are going to wait till TXIF falls down to 1. So that is the only thing you can do. You don't have to get an interrupt generated when you are transmitting. But if you still want, that is possible. So if you enable the interrupt, once you're done transmitting, you can have TXIF set with 1. So if you want, you can have a message printed and shown that the transmission is done. Clear? Okay. Now, the problem with this is, let me build this and show you the output. So for that, I should have QtCom also open. So tools, serial terminal. I will have a QtCom open. Meanwhile, I'll go to file and load the hex. So I have to first build. The build is happening. And if you see in the main function, I also have the logic of toggling the LED. This is not going to get affected this time. Okay. So file, load hex. Driver interrupt, distribute, default, production, the hex file. Okay. Just while transmitting and receiving, no need of interrupt, but when other events involved, that time we need to go for the interrupt. Yes. So for the sake of confirmation, if you want, you may have to need. Okay, let me open this. Then let me do the file and reload last. Now see, your test code is there. So I have configured this as a source of interrupt. So toggling of LED is happening without any disturbance. So if I transmit character A here, that gets collected by the microcontroller and it will be transmitted back. You can see the output here. Okay, so here you can see, oh, I'm sorry. Okay, so here you can see character A is displayed. Now I enter character B as an input. Oh, 1 second. So infinite times this is entering. One second. I hope I loaded the proper one. Okay, 9608. Then COM2, fine. I'm going to open this. Then file, configuration, COM1, okay, fine. Okay, PH is not equal to null, put care of PH. Okay, this I uncommented. I'm sorry. Okay, so this time it has to work fine. Let me clear this and clear this. Okay, so file, I do reload last. So UART test. You can see I enter character A is printed. I enter character B, B is printed. Now see, I'm entering hello. What are you able to see in the output? When I entered hello, did that hello get transmitted back? Only HLO. So in between, don't you see it is eating one character one after the other? After every character there, it is eating one character. So that's the drawback of QtCom. The drawback of QtCom application is it cannot work fine if it is configured in the interrupt mode. So that is why, as a substitute to this, we asked you to install Teraterm. So that's another serial transmitting application. Now you have to, the moment you launch the Teraterm, you have to click on serial. Okay. And you have to select COM1 and you have to click on OK. As of now, my access is denied because I have an application which is running COM1. So I'm going to close it. I'm going to stop using it. And then I'm going to do the setup again. 1 second. So let me open the Teraterm for another time. Okay. So here it is serial and you can click on OK. Still access denied. 1 second. Yeah, correct. It is COM2. I'm sorry. I'm trying for COM1. I have to set COM2. So COM1 on my terminal, that has to be COM2. Okay. So now you see the problem with Teraterm as an application is you don't have two different windows for input and output. So whatever window you are seeing here is the output window. Okay. There are no two separate windows. So for the input and output, whatever window you are observing right now, it's an output window. So whatever I enter will go. Whatever your microcontroller is transmitting, that will be seen here as an output. So please listen to the word, like the sound. I transmitted character A. So that got received by the microcontroller, that was transmitted back, which is what you are seeing here, A. Then I transmit B. So B is received by the microcontroller, B is transmitted back, so you can see in the output. So I transmit hello. So H, then E, then L, then L and O. Character by character it will be received, character by character it will be transmitted as well. Okay, and toggling of LED is happening by itself without any disturbance. So what I had to show you is the QTCOM has a small drawback that it cannot be configured properly if you are using it in interrupt mode. So you may have to go for another application. I'm choosing TerraTerm here. You can get n number of serial transmitting applications. Okay, so I have TerraTerm installed now. Whatever character I'm transmitting, that will be received by your microcontroller, and also when the microcontroller transmits it back, you are going to see it here in the output window. So that is how UART communication protocol is working. So one with the help of pooling, the other one with the help of interrupt. In TerraTerm setup, there is local echo option. Maybe it will work. The option which you previously opened. Okay. See, I can have only a receiver window. Local echo, if I say, okay, yeah, Y, U. So it is like local echo in the sense it just displays. It's not like an input window. You are using the same window to have both of your input and output displayed at the same time. What local echo does is, whatever you are typing, it will show it there itself, but it is still an output window itself. With the help of echo command, it is just able to display what you are trying to print. See, if I say hello at once, I want hello to be in an input window and again a hello in an output window. That is not possible. So you cannot see two different windows in that case. So you may get confused, which is why generally this will be turned off. So in that case, whatever input you are giving, so that will not be considered. Mean that will directly go to the controller, and whatever is received, that will be displayed here. Okay. Why it's skipping one character in QTCOM? Any freak? No. The problem is with the help of the application. So QTCOM is an application which cannot work fine with, let's say, I would say the interrupt method. So QTCOM cannot work. It's the drawback of the application. And 9600, yes, you could set manually. In this, I had an option, but I'm not getting it in this version. So earlier versions of the Pixim Lab, I had the option to choose what is the baud rate. But this time I'm not sure why. Like this application is not letting me choose whether it is 9600 or what. So it is fixed to 9600 only. Only this application. Yeah, so by default, this application, this microcontroller is working for 9600. Let me check. Yes, but software you can set on this board. See, on the software also, when you write 9600, your microcontroller is working with the baud rate of 9600 only, no? So when you say init UART by passing 9600, there will be SPI RG register which is working with 9600 baud rate. So on this application, you don't have an option, but in fact, the earlier version had an option to choose 9600 here as well, but I don't have it. Anyways, you are setting it in your software itself. So you have informed your microcontroller to work with 9600. So your CuteCom should be working with 9600 being the baud rate. For 20 megahertz, baud rate will always be 9600, right? No, Shreya. For 20 megahertz, you can choose any of a baud rate, which we saw it in the table yesterday. So out of all of it, so baud rate keeping high for 20 megahertz, I have these many options. And out of all of that, 9600 only has a smaller rate of error. So I can also take 19.2 for smaller error also. Okay. Whichever has a smaller rate of error, we generally fix that. So this is about the UART communication protocol, which established the communication between two chips of two different boards. It's an example of inter-board protocol. Any doubts in this? Okay. So take a break of 2 minutes. We will proceed with the next protocol, which is SPI. Okay. Can we continue? All right. So proceeding ahead, this completes the first communication protocol, which is nothing but UART. So who introduced the UART communication protocol? Which company introduced the UART communication protocol? Was it Bosch? Yes, it was by Intel. Okay. So UART is a communication protocol introduced by the Intel company. Now today we are going to start the next communication protocol, which is nothing but SPI. So SPI here stands for Serial Peripheral Interface. So this is the name of a protocol, and this protocol was introduced by the Motorola company. So SPI is a communication protocol. It was introduced by the Motorola company. So they wanted to establish the communication between two chips of the same board. So SPI is an example for intra-board protocol. So there you are going to establish the communication between the two chips of the same board. So the Motorola company people wanted to establish the communication between two chips of the same board, which is why they introduced a communication protocol called Serial Peripheral Interfacing. So coming to this protocol, first we will look at the introduction to the communication protocol. Then we will see the interfacing, how the communication happens between two chips. And then we will see the hardware configuration. Okay. Can't we print in CLCD using UART? First of all, obviously there is a controller already available in your microcontroller. And to have the communication between, you are not using the serial communication. So whether it is you, see, when it comes to the UART, okay, your question is, can't we print in CLCD using UART? The the first thing is you already have a CLCD which is done with the connection also. But if you are connecting it on board, like if you are bringing a CLCD separately, you are bringing the microcontroller, you are establishing the connection. So you may have to make use of UART. And in CLCD also, so CLCD should accept the data bit by bit. Okay, that's the thing. So see, you have to pick a CLCD which accepts the data bit by bit. So here I have 8 data lines. Either it uses all 8 data lines at once, or it uses a maximum of 4 data lines according to the CLCD we have brought. So you have to pick a CLCD which accepts the data bit by bit, and once you're done giving all 8 bits of data, you have to clock the enable. So you have to make the selection on the CLCD as well if you want to print some data on the CLCD with the help of UART. CLCD have a microcontroller, right? And pick microcontroller. So I need to keep ground between them. Yes, that is there. So you have to establish, you have to give a common ground. But I hope you're getting what's the problem here. So your CLCD is accepting the data 8 bits at once or 4 bits at once. It's something which is communicating with the help of a parallel communication. So more than one bit of data is being received at a time. You have to pick a CLCD which takes only one bit of data at a time. Okay. Okay. Fine. Microcontroller and microcontroller of CLCD chips are the chips on the same board installed. Can we use SPI? Okay. So, guys, all the communication protocols we are learning today or in our module are all serial protocols. So, they are going to transmit the data bit by bit only. Okay, fine. All right, so let us continue. So, I was talking about the SPI protocol. One second. Oh, yeah. So coming to the SPI protocol, so it's a protocol introduced by the Motorola company. So in this protocol, first we will start with the introduction, then we will see how the devices are interfaced, how hardware configurations are established, and how exactly is the data transmission happening. So we will see all of them in together coming to the SPI protocol. Now looking at the introduction, the very first point here it says the features of the SPI protocol, and the very first feature is synchronous. Now, what do you mean by synchronous? Communication is happening with respect to what? So, communication, yes, it is happening with respect to the clock signal. What type of communication protocol was UART? What type of communication protocol was UART? It's an asynchronous protocol. So this SPI is a synchronous protocol. So communication is always going to happen between the two devices with the help of a clock signal. Second thing it says is you are going to achieve full duplexity. Now in order to achieve full duplexity, how many data lines do I need? Yes, I need two data lines, one for the sake of transmission, the other to receive at the same time. So it's a synchronous communication protocol. It is going to help us achieve full duplexity. And this time, I have a synchronous protocol. So one of the device has to be generating this clock pulse. Whichever device is capable of generating the clock pulse, we call it as master. And if the device is not able to generate the clock pulse, we call it as slave. So master is a device which is capable of generating the clock pulse. Slave is a device which is not able to generate the clock pulse. So SPI is a synchronous communication protocol which helps us achieve full duplexity, and here it is able to generate the clock pulse. So generally both of them will not be able to generate the clock pulse. If both of the devices are able to generate the clock pulse, one will act as a master, the other will act as a slave. So both cannot be a master at the same time. So one acts as a master, the other acts as a slave. Now this communication protocol is also referred as single master multi-slave protocol. Okay, so this can also be referred as a single master multi-slave. So here it's the master who is going to communicate, and the master may want to communicate with multiple slaves. Okay, there can be multiple slaves in the device, and the master can communicate with any of the slaves in the network. So this protocol is called as a single master multi-slave protocol. Now, first of all, in order to achieve synchronous, I need a clock line, right? So I need one clock line in order to achieve synchronous. Then to achieve full duplexity, how many lines do I need? How many data lines? I need two data lines. Now, because I have multiple slaves, due to this, do you think there is a need of another line? Because I have multiple slaves. So there comes a need of another line called as the slave select line. Okay. So you need another line called as the slave select line. Now what is the slave select line is? You have multiple slaves in the network. Okay. So you may have more than one slave in the network. So you may need the particular slave to be selected. So you have an independent slave select line. Okay. So as per our discussion, if you see, you can observe there is one clock line, okay, two data lines and one slave select line. So this is called as a clock line, serial clock line. These two are two data lines. Then this one is a slave select line. Now the two data lines names are MOSI. First one is MOSI, which stands for master out, slave in. Second one is MISO, which stands for master in, slave out. Okay. So it is always with respect to the master we are addressing. So master in slave, master out, slave in, and master in, slave out. Now the names may get varied from one company to another. So if this protocol is used by the Motorola company, they call it as master out, slave in, master in, slave out. So if the same communication protocol some other company is using, so if the step remains the same, these pins can be referred as just data in, data out also. That is also possible. So different company people may refer the names of the pins in a different manner, but the functionalities are going to remain the same. Okay. So Motorola company says it as master out, slave in, master and slave out. So if National Institute people use this, they call it as data in, data out, but procedures are going to remain the same. So SPI stands for Serial Peripheral Interface, introduced by the Motorola company. And here I have got two lines for the sake of data transmission and reception. One is called as MOSI, the other one is MISO. I have one serial clock line and one slave select line. Any doubts in this? Okay. Now let us see an example here with respect to the hardware configuration. So this is an example for single master, single slave. Okay. What you are seeing as an example here is a single master, single slave. So master is the device which is capable of generating the clock pulse. That is why if you see the very first line, the serial clock, it is going out of the master and it is entering the slave. So it's the master who's always capable of generating the clock pulse. If if the device is not generating the clock pulse, you cannot call it as a master. So you address the device as master only if you are going to have the clock pulse generated. Okay, for N slave selects, right? Yes, yes. Okay, so I'm taking an example of single master, single slave here. So one clock pulse, clock line, SCLK, it is going from the master to the slave. Then I have MOSI. You can see in both the cases MOSI. MOSI stands for master out, slave in. So you can see the direction of the lines. It is going out of the master. It is entering into the slave. So it is MOSI. Then I have MISO, master in, slave out. So it is coming into the master from the slave. So you can see the direction. It is from slave to the master. Then slave select line, it is the line which is used by the master to select a particular slave. So it gets selected like this. Okay. So whichever whichever slave it wants to communicate, it is going to select it with the help of a slave select line. But what is the feature of SPI protocol? What is the advantage of using an SPI protocol? Come on. So what is the advantage of using an SPI protocol? What is the special feature of SPI? It is synchronous, okay, full duplex. I wrote something at the end. What is the special feature of SPI? No. Yes, so it is single master multi-slave. Okay. The special feature of SPI is it's a single master multi-slave protocol. So going ahead, I may not have to deal with a single slave. I may have to deal with multiple slaves. So I'm adding few more slave lines here. Okay, I'm adding few more slaves. So you can see the direction here. First, what you can observe here is I have a master, I have 3 slaves. So this is a single master multi-slave device. It is a single master multi-slave network. Now master can be your microcontroller generally. Slaves can be a device which is not capable of generating the clock pulse, maybe an RTC, a temperature sensor, a EEPROM, a flash memory, a DAC. So it can be anything. Okay. Now, whenever the communication is happening, it's the master who generates the clock pulse for every slave. So you can see the direction. From the master, it is going to the slave 1. The same clock line is going to slave 2. The same clock line is going to slave 3. So the same clock pulse will be shared, will be used by all the slaves. So anyways, the communication is happening between one master and one slave at a time. Okay. Can be sensors not available on the board as well. Can be sensors not available. Can slave sensors? That depends on the board you have selected. So some of the boards will have some slave devices on your board. Some of them may not have. So if you try establishing the connection on your own, you can add a slave of your choice. So some of the devices may not have. Master and slaves are microcontrollers. They need not be microcontrollers. Generally, masters are microcontrollers. Slaves will be some chips. So which is not independent. Okay, multi-slaves means multiple chips. Yes. I mean slave can be external sensors as well. Yes, that is possible, but it has to be on the board only. It has to be connected to one PCB. So both your microcontroller and your slave should be on the same board. Okay. So external in the sense it may not be available inside your microcontroller. You may have to connect it externally, but it has to be on the same board. So for example, if you take a breadboard, you are connecting the microcontroller, you are connecting the sensor of your choice, that is possible. If there are n slaves, master will have n pins of slave select line. Yes. Okay. So there are wired connection in the same board. Yes. So it is wired connection. PIXM is an example. PIXM is example as ADC is there and microcontroller. So ADC is a built-in block of your microcontroller. So ADC is a part of your microcontroller. Okay, so that cannot be used. How many slaves can one master have at max? It can have any number of slaves depending on the input output pins available in the master. Okay, can we proceed? Fine. So repeating again, I have one master with 3 slaves. So master is generating the clock pulse. So if master wants to communicate with slave 1, he gives that clock pulse. Master wants to generate with communicate with slave 2, it uses the clock pulse. Master wants to generate with slave 3, it uses the same clock pulse. Now master out slave in is one pin. So data has to come out of the master, go into the slave. So you can see the direction, it is going to slave 1, the same line is going to slave 2, the same line is going to slave 3. Then master and slave out. So master has to get the data from another slave. So you can see the direction, it is from the slave to the master. So all the slaves are giving the input to the master with the help of MISO. Then master uses slave select one line to select the first slave. Master select slave 2 with the help of SS2. Master selects slave 3 with the help of SS3. So master is going to select a particular slave with the help of the slave select line. Now assume master wants to communicate with slave 2. Okay. Master wants to communicate particularly with slave 2. First, master selects the slave 2 with the help of SS2. Once the master and the slave are connected, once the master has selected a particular slave, master generates the clock pulse. So Mosi is going to give the data to the slave. Miso is going to collect the data from the slave like this. So this type of configuration helps to establish a private connection between the two devices. So master is there. Master want to specifically communicate with slave 2. So it is going to select with the help of slave select line 2. At that point of time, slave 1 and slave 3 are not in contact. So they are out of the picture. That means they are not being disturbed. So they are not contributing for the communication. So slave 1 and slave 3 are busy with their own task. They are not disturbing the communication. Now similarly, if the master wants to communicate with slave 3, what will the master do first? So it is going to select the slave 3 with the help of slave select line 3. Slave 3 will be selected. Clock pulse will get generated. Mosi will work. Miso will work. Okay. So that is this hardware configuration which happens when a master wants to communicate with a particular slave. So it can communicate with only one, yes. So it can communicate as of now with only one slave at a time. Okay, so you may have multiple slaves in the network, but it can communicate with one slave at a time. So that is the single master multi-slave communication protocol. So as the number of slaves increases, the number of slave select lines also are going to increase. Understood this configuration? Now, what do you think is the disadvantage of this kind of a configuration? This kind of hardware connection, if you find, do you see any potential issues, means any problems? Any potential issues? More circuit connection, many lines. Exactly. See, whenever the number of input output lines are going to, sorry, whenever the number of slaves are going to increase, the number of slave select lines are also going to increase, isn't it? So as the number of slaves increases, slave select lines increases. In that case, let's say at some point of time it has an 100 slaved network. So there is a network with 100 slaves. So how many slave select lines a master will require at that point of time? It is 100 slave select lines. Don't you think it leads to hardware complexity at the end? Obviously, so that is always going to lead a hardware complexity. So it is going to be difficult to manage such kind of hardware connections. So if you see this kind of a hardware configuration. Now, just to overcome the drawback of this kind of circuit, so here the hardware configuration is very high, that as the number of slave select lines are going, sorry, as the number of slaves are going to increase, slave select lines are also going to increase. Okay. So this leads to a complex hardware issue at the end, and it will be difficult for anybody to manage, which is why we have to look at the positive part. We have to look at a circuit connection which helps us overcome this issue. I cannot go with this hardware connection if I have got more number of slaves. So as a substitute to this, to overcome the drawback of this hardware connection, we have one more connection, one more kind of a connection called as daisy chain configuration. Okay. So this is daisy chain configuration. Now what happens in daisy chain configuration is, this is trying to reduce the number of number of slave select lines. So I still have a single master with multiple slaves, but I don't have multiple slave select lines. Okay, so I don't have multiple slave select lines. There is only one slave select line for every of the slaves I have got in the network. Now here what happens is, the slaves are connected in a cascaded form. So it's like a daisy chain. I hope you know how daisy chains are linked with each other. Daisy flowers are linked with each other. So similar to that, there is a daisy chain configuration implemented here, and the connections between the two slaves are always cascaded. That means one slave, if you can see, clock is given commonly to all of the slaves. So Mosi of the master is going to the Mosi of slave 1. Miso of slave 1 goes to Mosi of slave 2. Then Miso of slave 2 goes to the Mosi of slave 3. And Miso of slave 3 is going back to the master. Now, what is happening in this case is, it's the master who is still capable of generating the clock pulse, but for the corresponding slave, the previous slaves act as a master. For the slave 2, slave 1 is a kind of a master. For slave 3, slave 2 is a kind of a master. So it's just the functionality which is making the slave behave as a master, but it is in fact still a slave itself. So there is master. From the master, it is given to the slave 1. From slave 1, it is going to the slave 2. From slave 2, it is going to the slave 3. Okay. So very similar to that. So now when master wants to communicate with slave 1, it generates the clock pulse. Mosi transmits the data to the slave 1. Now if slave 1 has something to be given to the master, it cannot give it directly. So whatever slave 1 has to give to the master, it has to first go to slave 2. From slave 2, it has to go to slave 3. And from slave 3, the data has to receive to the master. Similarly, if master wants to communicate with slave 3 directly, okay, master wants to communicate with slave 3 directly. So from the master, the clock pulse gets generated. So master cannot give the data directly to the slave 3. From the master, it has to go to slave 1. From slave 1, it has to go to slave 2. And from slave 2, it has to go to slave 3. That's something like this. Then if slave 2 has something to be given, so slave 2 has to give to slave 3. Slave 3 should give it to the master. So here, one drawback is, what do you think the drawback here is? Obviously, we have reduced the hardware configuration. The number of hardware lines are reduced. But what do you think is the configuration? Okay. It needs traverse all the slaves every time. Yes, with slaves. Yes. The problem here is with respect to the slaves. The data cannot be transmitted particularly to a slave. So privacy is not maintained. When a data needs to be given to a particular slave, it is not possible. So that privacy is achieved only by slave 1 when master is giving the data to slave 1. But the same case, if slave 1 wants to give the data to the master, then it cannot do it directly. It has to go through the other slave. Okay, that's a drawback. The advantage is hardware configurations are reduced, but the disadvantage here is, so whatever slave or master communication is happening, it is not private. It is not particular to one slave. It is happening with respect to the different slaves being involved. So privacy of the data is not maintained. Understood this? Okay. So that is the second hardware configuration of a single master and a multi-slave with the help of daisy chain configuration. Okay. Now proceeding ahead, after the hardware configuration, we have is the data transmission. So how is the data transmission happening? You can see I have one clock line and one slave select line. So one MISO, the other one is MOSI. So master out, slave in, master in, slave out. So similar to that of UART protocol, whenever you had to transmit some data, were you able to transmit it directly from a pin of a microcontroller? Were you able to transmit directly? No, right? So first you have to write the data to the buffer register. Then from the buffer register, where was it going? From the buffer register, where was it going? Yes, it was going to the shift register. Then from the shift register, data was getting shifted bit by bit. So here also the same thing happens. So first I have the data, whatever I want to transmit should be returned into the buffer register. From the buffer register, data gets returned to the shift register. From the shift register, data gets shifted bit by bit. Now assume master has the data 0x 100 is A and 0011 is 3, right? So assume master has 0xA3 to be given to a particular slave. So first this data gets returned to the buffer register. From the buffer register, it gets returned to the shift register. From the shift register, data gets shifted bit by bit. Now after I perform the shift operation for once, you can see whatever is in the MSB will go to the LSB of the slave. See? So whatever I had in the MSB, it came to the LSB of the slave. I shifted for another time. Whatever is in the MSB will come to the slave. So like this, for 8 bits of data from master to reach the slave, how many shifts I have to perform? Yes, I have to perform 8 shifts. So after I perform 8 shifts, you can see whatever is in the master is reaching the slave. So slave has now received 0xA3. Okay. So data is transmitted from the master to the slave. Now, I have, if you observe, whenever I was shifting the data from the master to the slave, did you also notice that the data from the slave was coming to the master as well? Did you also notice that whatever was in the slave was coming to the master as well? Let me repeat this. Let me show it from the beginning without before shift. So, one second. This is the data I have initially in the master. Yeah, so 0xA3. One MSB I shift, it comes to the LSB. Similarly, MSB of slave is received at the LSB of the master. You can observe. Then one more bit from the master when it goes to the slave, MSB of the slave comes to the LSB of the master. So slave initially had 0011 1011. So I say 0x3b. Okay, slave initially had 0x3b. So that has been given to the master. You can observe. So after 8 shifts, 0x3b will be inside the master. Don't you think I'm achieving full duplexity here? When master is transmitting, slave is receiving. Slave is also transmitting, master is receiving. So at the same time, master is transmitting as well as receiving. Slave is also transmitting as well as receiving. So that is how full duplexity is achieved. And you have two independent data lines for that. Okay. So the point to remember is when you have certain data to be transmitted, so you cannot transmit it directly. First data should be returned to the buffer register. Then it should be returned to the shift register. Then the data has to be shifted bit by bit. Okay. So that is how the data transmission is going to happen. And if you properly observe here, in the slave, I have the names given in a different way. So instead of MOSI and MISO, I have slave data in, I have slave data out, I have slave clock and chip select. Now the reason why the names are given like this is, The names given to the slave completely depends on the slave's manufacturer. Whatever names will be given to the slave, it completely depends on the slave's manufacturer. So, what happens with respect to the slave manufacturer is, it is telling whatever slave I'm devising is never going to turn out to be a master. So, the manufacturer says, if my device will never turn out to be a master, what is the point of referring it as master out, slave in, or slave in, master out? I will call it as slave data in, slave data out. So it is so obvious. So it doesn't have to say it as a master out, slave in, master in, slave out all the time. So manufacturer of the slave says, so I will so far refer it as master slave data in and slave data out itself. I don't want to give the different names. So that is what the manufacturer says. The names may be different, but the functionalities are going to remain the same. So Mosi here in the master acts as Mosi here in the slave also. Miso here in the master acts as Miso here in the slaves also. So just the names are different because that is being provided by the manufacturer of the chip. Clear with this? What is the control used for? So this is the control. Control here just represents that is capable of generating the clock pulse. Okay. So here the clock pulse is just received. It is controlling the clock pulse. And also it is able to select the slave select line. Clear with this? Any doubts? Yes, recording is on. Okay. Fine. The next we have to know is data validity. Okay. So when is the data return? When is the data read? So we have something called as data validity. See, whatever data you are going to transmit or receive is with respect to the clock pulse because this is one of a synchronous communication protocol. So when exactly is the when exactly is the data transmitted, when exactly is the data received is decided depending upon the data validity. Okay. Now coming to the data validity. So clock pulse will be generated by the master. Okay. And the SPI communication protocol, see, in case of UART, yes, you had data parity. There was a parity bit to make sure whether the data was received properly or not. So transmitter was transmitting a parity bit. Receiver was also calculating the parity bit depending on the data it has received. And when the parities are compared, if it is a match, it was concluded that the data transmit whatever is received is proper. But when it comes to the SPI, we don't have a triggering mechanism. We are going to generate the clock pulse and communication happens with respect to the clock pulse. So once the clock pulse is generated, any communication protocol can either be edge triggered or level triggered. So edge trigger means either the transmission or reception happens at the edges of the clock pulse, either at the rising edge or the falling edge. Else, there can be some communication protocols who transmit or receive with respect to the levels of the clock pulse. So some may transmit at the high level, and some may receive at the low level. So some may transmit at the low level, some may transmit at the high level. So data transmission and reception happens with respect to the clock pulse, either with respect to the edge triggering or with respect to the level triggering. Okay. Now the question comes is, what is when edge triggering happens, when level triggering happens? That completely depends on the SPI manufacturer. It depends on how the chip is working, which functionality has been incorporated. So here is an example which shows edge detection. So the communication is happening with respect to the edge of a particular clock pulse. Now, whenever the clock pulse is having a falling edge, okay, if the clock pulse is having a falling edge, whoever wants to transmit the data will be transmitting. Okay, so that is why you can see a change of data from 0 to 1 or 1 to 0. If there is any data to be transmitted, all the data transmission, whether it's the master or the slave, if it has to transmit some data, data transmission always happens at the falling edge of the clock pulse. Similarly, data reception, you are going to receive the data, you are going to read the data at the rising edge of the clock pulse. That is why you don't see the change of data here. If there is a 0, 0 will be read. If 1 is transmitted, 1 will be received. Okay. So data transmission and reception can either happen at the edges of the clock or it can happen at the levels of the clock. It depends from one device to another. So this example is showing the transmission and reception with respect to the edges of the clock. So data gets transmitted whenever you are going to identify a falling edge. This is the falling edge because the signal is falling from high level to low level. If the clock pulse identifies a falling edge, data gets transmitted, which is why you can see data in and out. There is a change of data from 0 to 1. Okay, data gets transmitted always, whether it's the master or the slave who wants to transmit, data gets transmitted always whenever I'm going to have a falling edge identified at the clock pulse. Similarly, when the rising edge is identified by the clock pulse, so all the data will be red. So you cannot see the change here. It is constant. So if there is a 1, 1 will be red. If there is a 0, 0 will be red. Okay. So all the devices are going to transmit when they identify a falling edge. All the devices are going to receive when they identify a rising edge. So that is data validation. Got this? Okay. So the next one is, when are we going to make use of the normal configuration? When are we going to make use of a daisy chain configuration? At what instances of time we will use a normal configuration, and when are we going to make use of a daisy chain configuration? So I think that we will see it in the next class. Okay, that one example I'll be left with, and we will see the rest of the things in the next class. I hope today's class has all been clear. Please wait till I give you the attendance. Okay. So here is your QR. Please have your attendance mark, then quit the session. Thanks for attending. We'll continue tomorrow. Thank you all.